Mm-hmm. Okay, no one joined, so let us start. So I'm going to record the video for the students. So today we are going to focus on the week number 5, the fluid mechanics, and the topic is the application of the fluid static and the dynamics. And the lecture 1 was about the fluid statics application, and lecture 2 was about the conservation of momentum, and lecture 3 was about the Bernoulli's equations. So this week number 5 was actually focused on the problem solving session. So today I have a lot of questions as well as some concept regarding the application of the Bernoulli's equations. So let us go one by one. So as we have discussed earlier, so Bernoulli's equations, the pressure head and the velocity head and your datum head, or you can say the elevation head, is equal to constant, that is your the combination of all three head is your total height. So we have earlier seen these things, and another concept comes based on the Bernoulli's equation is the pitot tube concept. So how we will calculate the velocity using the pitot tube, or actually using the pitot tube we calculate the pressure, actually pressure head. Based on the application of the Bernoulli's equation we can calculate the velocity. As you can see here, this is the formula, and here also you can see the stagnation pressure, how you will calculate the stagnation. And here the stagnation point is this is your pitot tube, and this is here is the piezometer. So as you can see here, the comparison up to that, from here to here is your velocity head, and below one is your potential or static pressure, as you can see here, and the above one is your velocity head. So based on this concept we can calculate your stagnation pressure. From here we will calculate your pressure, the static pressure, and using this, that is the from piezometer will calculate the static pressure, and using the your pitot tube will calculate the stagnant pressure, and from here the correlation is there, as you can see here, and from here we can calculate the velocity. So basically here we will apply the, this is, let us suppose this is point 1 and point 2, here is the velocity is 0, so once you will apply the Bernoulli's equation here, what will happen, the velocity component v square by 2z will be 0. So only right hand side, that is point 1 and point 2, if you want to apply here. So let us suppose here this is your point 1 and this is just immediately here is point 2. So at point 2 some velocity is there, but here is velocity is 0. So once you will apply, and the velocity at that point is v. So using this we will calculate, using this concept we will be able to calculate the velocity from your pitot. So here we can understand something. So P here is your static pressure, and rho v square by 2 is your dynamic pressure, and rho z is your hydrostatic pressure. So lot of here I have written already the concept behind. So as you will, I will not go through all points, but after uploading the video you can go, or I will upload also the content in the Google Drive, so you can go one by one. So now let us go on the next one. So here you can see the stagnation pressure hold, this one, and is the static pressure hold is this one. So this is the pitot static probe. This is the static, dynamic, and the stagnation pressure measurement using the piezometer tube. This was the piezometer tube. Here the figure is about the pitot static probe, showing the stagnation pressure hole, this one, and two of the, and here is the 5 static circumferential pressure hole, but 2 is visible in this side. Okay, the same thing is here. So now let us move with the another concept. So one here you can see the things which is very important. This line, the stagnation pressure represents the pressure at a point where the fluid is about to a complete stop isentropically. Means here the why the term used isentropically here. So let us understand the meaning of the first what is isentropical. Complete stop isentropically means basically in the fluid dynamics or fluid mechanics, the meaning of complete stop isentropically is there is no heat transfer or the friction loss. As you can see here, no heat transfer or the friction loss. This is the main concept behind this isentropically. So here the stagnation pressure represents the pressure at a point where the fluid is about to complete stop isentropically, means there is no loss here. The meaning is there is no loss, means if there is no loss, then what will happen? Your whatever the kinetic energy will completely convert in the your pressure energy or stagnation pressure, you can say. So this is the, because there is no loss. If there is no loss, so all energy, let us suppose fluid is coming from this direction to this direction, once the fluid is reaching at that point, it is completely stopped, means what? And there is no loss. If there is no loss, so energy will convert in the another energy, so it will be converting. This is the assumption here. Little bit it depend on the instruments, how much loss and or whether the loss is negligible. It's depend on the instrument condition. But for the derivation purpose or for the conceptualization purpose, we are trying to understand here the complete stop isentropically. Meaning here, the all kinetic energy will convert in your the stagnation pressure or stagnation energy or static energy, you can say also. So now let us move on to another concept. Okay, so the drilling, once let us suppose you have one pipe and you want to insert a piezometer. If you want to insert a piezometer, you need to drill in the pipe, you need to drill and then insert, because the drilling will affect more. The drilling method or the sharpness of the drilling will affect more. As you can see here, the height here is the effect is, as you can see here. So once we will go through this statement one by one, so definitely you are able to understand. So before moving ahead on the problems, so let us discuss about the pipe roughness and the velocity, pressure. So you know already the pipe roughness, actually this is from the friction between the fluid as well as your pipe material. If the pipe material will be smooth, the roughness will be less, the roughness effect will be less on the fluid flow. Now the velocity and pressure we have already discussed. Here one thing is very important. Actually in the fluid mechanics we quantify the effect of roughness using the Darcy-Weisbach equation or Colebrook-White equations. So remember these things also. Okay, now let us begin with your question. In which of the following, we have the four options and questions. In which of the following measuring device which use the Bernoulli's equation? So Venturi meter, orifice meter, Pitot tube, all of them. So here is the meaning is, in which instrument we calculate basically here the ask question is asking about the application of the Bernoulli's equation. So whether we use in the Venturi meter, orifice meter, Pitot tube, or all of them. The question is this. So definitely, as we have seen in the earlier classes, so we apply for calculation the discharge or whatever, depends on the question. We apply the Bernoulli equation in Venturi meter, orifice meter, Pitot tube, everywhere. So all options will be correct. So now let us move with the next one. In case of closed cylindrical vessel, in case of closed cylindrical vessel selected at the top and bottom of the air before rotation is filling the blanks, the volume of air after. So let us suppose you have one vessel, cylindrical vessel. So let me just draw. You have this one, and in this you have air in the vessel, and this is tightly packed from both sides, that is sealed from both sides. There is no air pass and no leakage. So first case is this, and second one is you have the same container, same vessels, and you are going to rotate. You are going to rotate this one. So now asking about before the rotation and after the rotation, the volume effect. Volume effect before the rotation and after the rotation. So what will be the effect? So definitely if the tightly sealed, there is no loss of the air, because here is the air, not we are talking about the liquid. So definitely it will be the equal. So remember this. Now the another question is, a flow has diverging straight streamline. Here the question is about the diverging straight streamline. If the flow is steady, the flow option A is a uniform flow with local acceleration. Second one is the has the convective normal acceleration. Third one is the has convective tangential acceleration, and fourth one is the has convective normal as well as tangential acceleration. So which option will be correct? Here you have the if flow has diverging straight streamline. Remember please, question is talking about diverging. So a straight line is like that. That is your diverging straight streamline is like that. Something diverges. Flow is diverging. The straight line. Remember please. I'm not able to draw. Today I have not pen with me. So this is a diverging. So what will happen? So whether the convective normal acceleration or tangential acceleration, or flow is steady, another condition is there. So definitely local acceleration will not be there, because of local is due to your the effect of time. So here is steady, so there is no meaning of your local acceleration. Local acceleration will be zero. But what about the convective, whether normal or tangential? So you have to first understand about what is normal acceleration and what is tangential acceleration. When normal acceleration will be generate, and when the tangential acceleration will be in the flow. So this is very important. So as you know, the normal acceleration means what? If the water is flowing like that, then something, the flow is going to accelerate in this direction. This is the normal. And what is tangential? The flow is going to accelerate in the flow direction. This is tangential. So if the straight streamline, if the straight streamline means what? There is no curvature. If there is no curve, so your fluid will not move in the lateral direction or normal direction. So here what will happen? The normal acceleration will not be present. The normal acceleration, convective normal acceleration will not be present. If your the streamline will be like that, that is the curvature, then as you can see, it the fluid is moving in the tangential, that is in x direction also, and in the y direction, that is the normal also, in this direction also, because fluid is moving from here to here. If the straight, I draw the straight streamline, then the curve streamline. So as you can see here, the fluid moving from here to here only in the tangential, but the fluid once moving from on the curve path or the curve streamline, what will happen? The flow is moving in the two directions, straight as well as little bit above. That is the normal. So in that situation, the normal acceleration will be present in your fluid flow. But here is the straight, so definitely your answer C will be correct. So here is the explanation is very important. So I have explained, I think, everything. So but I want to explain little bit concept here. So as we have discussed in the question, the streamline represents the path of the fluid particle, as you know already. Sir have already discussed in the class. If the streamline is spread apart, that is the divergence, the available flow area increase. Means, let us suppose initially the flow was like that, but somehow your flow is diverging. The flow is diverging like that. Means here the area was, let us suppose at that place area was A1, and here the area A2, because it is diverging, as you can see, because it is diverging. So if the area is A2, that thing here is written, if streamline diverges, the available flow area will increase. For steady flow, the continuity equation must be whole. For any flow, your continuity equation must be whole, means your area and velocity should be constant. And if the flow is incompressible, then rho also will not consider the rho. So here is the compressible flow, rho AV should be constant. If the fluid is incompressible, then we will not consider here A, that is rho. A and V should be constant. So if area is increasing, in that case, if area is increasing, what will happen? Velocity should be decreased. Then only the multiplication will be the constant. So what will happen? Velocity reducing. As flow is diverging, velocity is reducing. Means Velocity is reducing means what? The acceleration. The acceleration definition is what? The change in velocity. So definitely here in the change in velocity with respect to, and when we use the convective term, when your velocity is changing with respect to space, not time. So definitely as you are moving in the forward direction, or as if I draw here the x-axis and y-axis, so as you are moving in the x-axis, the velocity is changing. The velocity is changing means the acceleration, your flow have the acceleration. Yes. So this is convective acceleration will be here. Now, so the velocity magnitude is changing and the convective tangential acceleration. Why tangential? Because in the flow direction your acceleration is happening, not on the curve path. So this was the concept. And here also I have written why not the normal acceleration, because it is linked with your curvature. So this question was about a straight streamline, so there is no curvature, so no normal acceleration. Always remember this. Now another question. A flow has parallel curved streamline. This question is about the curved streamline and is a study. Here also the flow is a study. This flow has option A, tangential convective acceleration, local acceleration, normal convective as well as local acceleration, and normal convective acceleration. So you have the four options. Yes, recording is going on very well. Okay. So here is parallel. Here is two term very important. That is the parallel and curve streamline. So like that. This is parallel. Similar. Like that. Here I am not able to draw very precisely because of, but it is like that. Remember. Let me just okay. So like that. Now, so whether this situation have your tangential convective acceleration, local acceleration, or normal convective acceleration as well as local and convective and normal convective acceleration. So similar concept here you need to understand, but here is parallel. So what is parallel means in terms of your mass flow? If you want to apply here the concept of continuity, then what should be the concept behind the parallel means here, the parallel curved streamline? So the explanation also I have given. Let me just discuss. So a question is just state about the flow is studied, so definitely your local acceleration will be 0. So this option will be option B and C will not be correct anyhow, because these both have the local acceleration. So whether option A and B, which one? So streamlines are parallel means the parallel streamline means the flow is uniform in magnitude. And how uniform? Why uniform in magnitude? For that I have also the concept. For an incompressible fluid, the volume flow rate or discharge you can say between two streamline must be remain constant. Meaning if the flow is parallel, the here and here, so whatever the flow is going in this direction, that is the here is discharge, here another discharge. So this statement is talking about the volume flow rate between two streamline must remain constant. This is the continuity equation where the whereas the area of cross sectional between streamlines. So if the parallel, then area at both, here area let us suppose A and area here also is A. So if area is same and velocity is same, definitely Q will be the same. So meaning if velocity is same, area is same, means we can say this uniform flow, uniform in magnitude. So the statement is written, the parallel streamline means the flow is uniform in magnitude. Why uniform? Because area is same, or if area same, velocity will be the same across the streamlines. So velocity magnitude does not change along the streamline. So velocity magnitude does not change along the streamline, so no tangential convective acceleration. Again think, if this is a curved streamline like that, I'm not able to draw very precisely here, first try to understand. Let me just draw, yeah, like that. So everywhere the area is same, and definitely if the area here is here also area, here also area, everywhere the area is a, and velocity also will be the a. Velocity also will be the, if here is v, here also v, here also v, here also v, everywhere v. So it means if the velocity is v and area is similar, so and velocity also similar, means there is no change in magnitude of the velocity in the direction of flow. So there is no tangential acceleration, but you have the curve streamline, and due to the curvature of a streamline you have the normal acceleration because of your centrifugal force. That is, the acceleration value will be a is equal to v square by r. This value will be, and r is the radius of curvature, that is this one, this radius, this is the r. Remember this. So here the definition is written, straight streamline and curved streamline, everything, what is convective acceleration, straight streamline, curved streamline, normal acceleration, straight streamline, everything is here. So everyone can go one by one once I'll upload the PDF. Now the next question is the flow in a river during the period of heavy rainfall. This is the practical question. The flow in a river during the period of heavy rainfall. Option A, the steady, non-uniform and three-dimensional flow. Option B, the steady, steady, uniform and two-dimensional. Option C, unsteady, uniform and three-dimensional. Option D, unsteady, non-uniform and three-dimensional. So which option will be correct? Question is talking about the flow in the river during the heavy rainfall, or you can say in the flood period, during the monsoon period you can say. In the monsoon period, you know very well, the flow is definitely very very, let me just draw the figure. So let us suppose monsoon period is start from here to here. So up to before the monsoon period your flow will be like that, but in the monsoon period your flow increasing like that, and then it will be decrease, and then it will go like that. So in monsoon period flow is very very high, as you know already, because of the heavy rainfall here is written. So flow will be the unsteady, as you can see the discharge, if that is discharge with respect to your time. Time means month you can say consider here, or day also consider. So as discharge is changing in the same river, then what will happen? Then the, with respect to time, your flow velocity, everything is changing, so unsteady. Definitely it will be the non-uniform, because it is the discharge is increasing over the period of time, and in the heavy rainfall there is lot of turbulence, so definitely, of course, the three-dimensional flow. So option D will be correct here, remember. Now question 6, if the flow is irrotational as well as steady, then it is known as, the flow is irrotational as well as steady, the two condition is here is given. So this flow will be non-uniform, one dimensional, potential flow, or none of the above. Which option should be correct if the flow is irrotational? Yes, if the flow is irrotational and steady, the flow will be potential flow. Why potential flow? Because in irrotational flow, the vorticity will be the zero. In the irrotational flow, the vorticity will be the zero in everywhere in your fluid. In the flow domain, in such flow, we can define velocity potential like this: divergence of your potential function. Now, and why potential? Here is the, if the irrotational, why we are particular with the potential name, the reason behind it. In irrotational flow, the velocity field has a special properties, which is divergence of velocity is equal to 0. This means the velocity vector field is conservative, just like the gravitational and the your electrostatic field, as you have studied in your mechanics, or you can say in your 12th class. So in mathematics, actually we write the conservative vector field in terms of gradient of a scalar potential function. So from here, from your mathematics, we link with your the similar thing. Here is also, this is mathematics. The vector is equal to the divergence, the your divergence of potential function, or the gradient of a scalar potential function. So the similar terminology we are using from mathematics. So here details are given already. You can go one by one. Now another question is question number 7. The momentum correlation factor beta is used to account for change in the direction of flow, change in total energy, non-uniform distribution of velocities in inlet and outlet sections, and change in mass rate of flow. So why there is no student joined today? What's happening? The momentum correction factor beta is used to account for change in flow direction, change in the direction of flow, change in the total energy, non-uniform distribution of velocities in inlet and outlet section, change in the mass flow rate or mass rate of flow. So here the momentum correction factor is y, as the flow velocity, if I draw here the velocity diagram, this is depth, the flow variation, the flow velocity variation in with respect to the depth. So it is like that. This is your velocity. So as you can see, as we are moving from upward direction from your bottom, if this is channel, or you can say if this is pipe, so if the water is flowing fully, completely filled, so we are here, I am drawing the half part, this part. If this is D, so this part I am here I am drawing. So as we are moving from this your surface of the pipe, your velocity is increasing, but correction factor, let us suppose if you want to calculate the discharge, so you will use the area into average velocity. Whatever you will use the velocity here, this should be the average, but you know the velocity is vary from point to point, from your wall to your midsection in the pipe. So considering these things, once you will convert this your, if this is laminar flow, let us assume the laminar flow, fully developed laminar flow, so it is parabolic. If the parabolic, this is your parabolic graph. So for parabolic, when you will convert in your average, so this will be like that. Like here, average means what? Everywhere your velocity magnitude will be the same at every place. So this much you need to correct here, this much you need to correct here. So for this correction we use the momentum correction factor for accounting the parabolic to your the uniform velocity distribution. So here the options would be non-uniform distribution of velocity at inlet and outlet section. This option will be correct. So hopefully you will understand. Now the continuity equation. So continuity equation is the given equation del u by del x, del u by del y and del w by del z is equal to 0. So three-dimensional continuity equation is given here, and it is valid for what? It is not valid for unsteady incompressible fluid, option A, and option B, it is valid for incompressible fluid whether the flow is steady or unsteady. Option C, it is valid for steady flow whether compressible or incompressible, and option D, it is valid for ideal fluid flow. So four option is given. This is four option is given. So based on the option, we just try to think which option should be correct, whether A, B, C. The continuity equation. Continuity equation, this is also A1 B1, but here is the in the differential form is given A2 B2. This is also your continuity equation, but this is more general. Once we are talking about the differential way, so we can write the continuity equation like that. So one thing you can observe, the rho is constant. If the rho is constant, so we take the common from each term and we can say, or we can make it the rho free. So here is there is no rho in any term. So means it is incompressible. So this equation is valid for incompressible. Now, whether any the t term, that is the time variation with your velocity, no. So it is also valid for your steady. This is also valid for your steady. But we can use for this is non-steady, unsteady, no, because for unsteady we have to term t. So is not valid for unsteady? Yes, correct. Incompressible fluid, no, not valid. Here, if at the place of in, if the option was compressible only, then it was correct. So now let us move on the next one. Is valid for incompressible fluid whether the flow is steady or unsteady? No, only unsteady, not unsteady. Is valid for steady flow whether the compressible or incompressible? So this should also try to understand, and is valid for ideal fluid flow only. So four options we have. Okay, here this statement is talking about the momentum correction factor, not about this equation. So once you will go through this document, so please remember. So this is your about the momentum correction factor. So only we have the one option remaining here, that is your option D is valid for the ideal fluid flow only. In ideal fluid flow, we consider the things, the flow is steady, incompressible, so remember please, or let me just check whether Okay, here in this question we can make some corrections. So if we can make some corrections here, it is valid for incompressible fluid and the not whether the flow is steady or a steady incompressible fluid, you can say. Steady incompressible fluid. So remember please, we have to make some corrections. So option B will get this. Now let us move on the next one. Which of the following is an example of free vertex flow? Which of the following is an example of free vertex flow? After this question, okay, I'll take the some 5 minute break. Which of the following is an example of free vertex flow? A whirlpool in the river, flow of liquid through a hole provided at the bottom of a container. Option C, the flow of liquid around a circular bend in a pipe. All of the above. Which of the following is an example of free vertex flow? So definitely free vertex, there is no external force you are imposing for the vortex formation in the fluid flow. So here of course the correct answer will be the all, that is D option. Okay, now I'm going to take break 5 minutes. So if anyone want to go,
पे ये सब्जेक्ट कौन सा दिन में है? वो लिखा है फ्लूवियल ना, मंडे ट्यूसडे फ्राइडे, फ्राइडे वाला तू कर देना, ठीक है? हाँ चल आज मैं कर रहा, मैं जा रहा हूँ, आग जब कर रहा हूँ।
Okay, let us start with the new question. The question number 10. The vortex potential exists for, the velocity potential exists for the flow of a perfect fluid only, the steady irrotational flow only, all irrotational flows, all 3D flows. So which option should be correct? The velocity potential exists for only all irrotational flow, remember please. What is free vortex? No external force, inviscid flow, everything is written. So if we will go one by one, definitely will go. Okay, so here is the question, and also I have the solution also. So let us move. Water in an open channel is held by a sluice gate. This is your sluice gate. Assume the flow at a section 1 here, the flow at a section 1, this is your section 1 is given here, and 2 is incompressible. Assume the flow at section 1 and 2 is incompressible and uniform, and the pressure distribution are hydrostatic. Pressure distribution are hydrostatic. Calculate the horizontal force per unit width. That is, width here is just, you need to assume 1 because you need to calculate the per unit width in kilonewton per meter on the gate. On the gate or when it is open. When it is open. Okay, and here the your depth is given. The flow depth here is 3 meter. Here flow depth is 0.429 meter, and here flow depth, here your velocity is 7 meter per second. Here velocity is 1 meter per second. So now you can just try to calculate. Horizontal force per unit width on the gate. So this is very important question, very conceptual question as you can see. So I have here step by step solutions. So how? First check the continuity, whether the continuity is valid at the both places. Yes. So V1 D1, this is your V2 D2, this is your why D1, because area is what? Area is your width. Width already you know, 1 is given, and depth. So depth, so if 1, so that's why V1 D1. There is no meaning of 1 in the multiplication, so that's why 1 and 3, 7 into your depth. So in step 2, what you will do? Apply momentum equation in the x direction. Now you are going to apply the momentum equation in the x direction. Means the hydrostatic force will act in this direction, here in this direction. Remember, now Due to the gate also the force will act in this direction. Okay. Another one, your momentum, that is force is equal to rate of change of momentum. So rate of change of momentum is your change in velocity into rho into q, that is rho q velocity means m dot. So here change in velocity, we are changing momentum, so change in velocity, so that is your v2 minus v1. So you need to calculate this one first, the hydrostatic at section 1, hydrostatic at section 2, and and then the force by gate, and we need to calculate this one. And you know already the velocity and v1 v2 and discharge, you know already, the 3 is almost same. So now how you will calculate your hydrostatic force? So you know one thing, let me just explain here. So here is the distribution will be like that. If this is, so here distribution will be, hydrostatic pressure distribution will like that. So if this is D2, so it will act here, the pressure, and force is equal to pressure into, the force is equal to your P into A, and A already you know, width, W into D, that is your depth. So W is 1, so only D will be remain. And what is pressure? Half the area of this, half rho G D, and for area also equal to D, so you will be D and D square, so half rho G D square. So as you can see here, half rho G D square is given here. So put the value and get the equation. Similarly for downstream also. So now, and what is rho q1 q2 already you know, v1 v2 already know, so everything is here. Now the each value, the 400, each value you need to put in this equation, and after the final calculation you will get this value. So very important, remember please, this question is very important. Especially you can think about this is the analytical type question, so you can get exam point of view also very important or your final exam also very important. So remember these things. So next question is, a triangular gate, base 2 meter, height 1.5 meter, lies in a vertical plane. The top vertex is 1.5 meter below the surface of the tank, which contains oil of specific gravity 0.8. Considering density of water and acceleration due to gravity to be 1000 kg per meter cube and 9.81 meter per second square respectively, the hydrostatic force in kilonewton exerted by oil on the gate. So here question is, a triangular gate, base is 2 meter, remember, and height 1.5 meter, lie in a vertical plane. The top vertex is 1.5 meter below the surface of the tank. If this is surface, which contain the oil. This is oil. Okay, so this is your base of the triangle. Okay, and this is your 2 meter, base 2 meter, this is your 2 meter, and height is 1.5 meter. Height is 1.5 meter, and the from top the distance is 1.5 meter from the top. So this is the question. Now this is 1.5 meter, and the specific gravity of the oil is 0.8. Okay, considering the density of water and acceleration gravity, everything is constant, so 1009.81. The hydrostatic force you need to calculate here. So what is force, hydrostatic force in such situations? So force is equal to rho g h bar into a or y bar, you can say. If we are going to consider the depth, as we can say y bar or h bar, whatever. So this is your final expression for the force, as sir have taught in the class also. So base is 2 meter, height is 1.5 meter. So area of the triangle will be half b into h. So it will be 1.5 meter square. And the depth is given 1.5 meter. So centroid of the triangle, how much? This is h means what? This is your centroid. So this will be the h by 3. Let me just, this is 1.5. If this is triangle, so from here to here, h by 3. So the top vertex is 1.5 meter, though the diagram will be just opposite. The vertex will be like that, not the base. Here is vertex, remember please. You can do the similar mistake in your final exam, so you not do like that. So just the mistake of the reading mistake, so remember please, it is like that. So this is 1.5 meter below the vertex, not the base. 1.5. So now, and from here, from the vertex is your 2h by 3. If this is h, 2h by 3 means, so from here also this will be your centroid. So from here to here 2h by 3, 2h by 3, and this is 1.5. So that thing is written 1.5 plus 2h means 1.5 is the h. This value is how much? The 1 point. The distance from the free surface to vertex is 1.5. Also the depth is also 1.5 in the question is given. So 1.5 2h by 3 means, and once you will calculate you will get 2.5. Now everything you know. The rho will be the 800, g will be this 9.81, and your area is 1.5 meter square, and your y bar is 2.5. So your answer will be 29.43. For a student who not know the specific gravity, how you will calculate the density. So a specific gravity is what? A specific gravity, if it is given for oil, So rho of oil, that is the density of oil, is equal divided by density of standard fluid. So here standard fluid we are considering, actually in the fluid mechanics water, most of the questions we can consider. So this is 0.8 and water, the water density is 1000. So here is 1000. So actually a standard liquid we consider the this specific for calculation of, if it is not written the relative specific gravity or something, only specific gravity is written, always consider the water, that is 1000. So 0.8 into 1000 you will get the 800. Now the next question, determine the position of the center of pressure of a circular plate of diameter 1.5 meter which is placed vertically in water in such a way that the center of plate is 3 meter above the free surface of water. So we need to calculate here the center of pressure. The center of pressure and the situation is given here. Determine the position of center of pressure of a circular plate of diameter is 1.5 meter. The diameter is 1.5 meter. Okay, which is placed vertically in the water in such a way that the center of plate is 3 meter below the center of plate. If this is center of plate, this is below the 3 meter of your from the free surface. The question is this, what is center of pressure formula? And also you need to understand the definition also for center of pressure, not the formula. Not only focus on the formulas, so you have to understand the concept also. The center of plate is 3 meter below the free surface of the water, is the question is like that. Now you know already the center of pressure is always lie below the center of gravity or the center of the plate, you can say. Here is the center of pressure, Cp. So definitely it will be the more than 3. We have the 3 options, this and this. Which option will be correct? So this should not be correct. Out of 3, anyone we can select. So which one? Anyone may be correct. Which one? So for that, the center of pressure calculation is, that is whatever I have written the Cp, here is Hp is written. Hp is equal to H bar divided by this center of, that is the moment of inertia with respect to the this axis centroid, the second moment of area, second moment of area about the horizontal centroid axis. So diameter is 1.5, radius will be the 0. Definitely half of the your, of course half of your diameter, and the centroid depth is 3 meter already in the question. So what will be the your Ig, that is second moment of area, the pi d4 by 64. Once you will put here, you will get this one, and after the only the calculation. So finally your answer will be the 3.0 6468. So you can match. Now another question is very very important. Here you have in one question three sub questions. Calculate the pressure due to the column of 0.3 meter of water, oil of a specific gravity 0.8, mercury of a specific gravity 13.6, and take the density of water 1000. Calculate the pressure due to the water column. So you have the water column of, let us suppose you have the water column is 0.3 meter. This is 0.3 meter. Now you need to calculate the pressure. So pressure you know already, the hydrostatic pressure we will consider here. So half rho g h. So everything is same, expect your rho. For each, rho will be different. For first case, that is water case, 1000. For second case, it will be 800. For third case, 3613600. So I'll calculate for the first one. Let me just calculate. Half into 1000, or I am going to consider 10 for the calculation simplification. H is given 0.3. So once I'll remove the point here, it will be the 10, and 10 to 10 we can cancel out, and here we can write very easily 5. So what should be the correct answer? Just please you can try. Calculate the pressure due to the column of 0.3. Oh, so we are calculating here the pressure due to the column on the base. If you are calculating the on the base, so it will be not half. Once you will calculate the water, that is your pressure on something, let is suppose you have one support and the water in this side. So when you will calculate the pressure, then you will, your pressure distribution will be like that. When you will calculate on the base, then only not half. On the base, rho gh only, not half. So here 10 will be remain. So around 3000 Newton per meter square. This is your pressure. So here answer is given in centimeter. So what you will do for centimeter, you will write here 40, 12340. Then you can write this meter into centimeter, and once you will convert, then 0.3, 0.3. So this one, or 29 you can say, maybe the option A and option D correct. Once you will calculate these other two parameter, mercury as well as, for mercury it will be, once you will calculate for liquid, that is oil, you will get, so for oil it will be 800 here. So 800 means 24. So in both 0.245, okay, two options here is same, I think, 2943, 2943. Okay, this one, this will be the option A will be the correct, because rho for oil is 800, G let us assume the 10, and 0.3, 0.3. So once you will calculate, you will get 8 3s are 24. So the similar thing for centimeter square. So here is 0.3, so means 0.24 something. So this one 0.2354. Why it is little bit less by 2 point? Because we are using the 10 here. Once you will multiply something 9.81, you will get definitely this one. So option A will be correct. So remember please. Now the next question is, a horizontal water jet with a velocity of 10 meter per second. A horizontal water jet with a velocity of 10 meter per second and cross-sectional area of 10 mm square strike a fixed plate held normal to the flow direction. Find the total force acting on the plate. Take the density of water is 1000 kg per meter cube. Option 1 kilonewton, 1 newton, 10 kilonewton or 10 newton. Which option may be correct? A horizontal water jet with a velocity of, horizontal water jet, horizontal water jet with a velocity of 10 meter per second. 10 meter per second velocity is given, and the cross sectional area 10 mm square. This area will be 10 mm square. Strike of fixed plate, here is fixed plate is and normal to the flow direction. Find out the total force acting on the plate. So how much force is acting on the plate due to this jet? So the force is rate of change of momentum, you know already. So rho A V or delta V. So here V is this and the final velocity is 0. So only V will be remain. So rho is 1000, area is 10 mm square. So for meter you need to write in 10 to the power minus 6 into V. V is your 10. So how much? Anything else? No. Rho AV, this is your pressure, and rho AV square, not V only. Your force will be the rho AV square. So after the calculation you will get, here is the 304,560 and 10 to the power 6, so only one will be remain, so 1 Newton, so not kilonewton, 1 Newton. Option B will be correct. Your force will be, remember, m dot rate of change of mass velocity, so m dot will be your rho q. Rho q means rho a v and another v is rho a v square, remember. Now the next question is, the diameter of a pipe at a section 1 and 2. Hello, hello Dinesh Kumar.
Sir,
Okay, okay, I am audible, very clear.
yes, you are audible, sir.
Okay, okay, and slide is visible. Question number 7. Question number
Yes, sir,
7.
it is
Okay, okay, very nice.
visible, sir.
Okay, okay, very nice. Thank you. So we actually, I have already recorded the video from, I think, 1 hour and 40 minutes, because I am teaching from last 1 hour 40 minutes from 7
Right,
p.m.
sir.
7 p.m. So only
Right, sir.
20-minute classes remain. So let us discuss the question.
Right, sir.
Very important. So once I'll upload the video, you can go through all questions. So I have solved a lot of questions. Let me just show you very quickly. As you can see here, some I have also discussed about your pitot tube concept. So you can go one by one, right? So
Right, sir.
without any delay, let us discuss on the question number 7. So question number 7 is about the diameter of a pipe at a section 1 meter, at a section 1 and 2 are 10 centimeter and 15 centimeter respectively. So you have this type of, okay, let us read the final question. And given the velocity of water flowing through a pipe at a section 1 is 5 meter per second, determine the velocity at section 2 and discharge flowing through the pipe. So you have some tapered situation. Here is section 1 and section 2. Let us write like that. And here your 10 centimeter diameter is 10 centimeter, and here is diameter your 15 centimeter. So now then velocity is given at the section 1 is 5 meter per second. Here is the velocity is 5 meter per second. So actually I don't have pen today, so I am not able to write very clearly. And you need to calculate the velocity at 2 and also the discharge. So discharge you can very easily calculate. So please, if you have your pen and copy, you can try within 2-3 minutes. Simple continuity equation you need to apply here. So first you need to calculate the area here. As you know, the discharge is equal to area into velocity. Area into velocity, so area will be your pi by 4 into d square. Pi by 4 into d square into velocity. So from here you can calculate very easily your discharge. Now from the continuity equation, A1 V1 is equal to A2 V2. So from here you can calculate your V2, that is V2 at the velocity at section 2, because area you know everywhere. So this is with calculative question. So are you solving, or let us move on the next question?
Yes, sir. You can move to the next question. It's
Yeah,
easy.
yeah, very,
Even
very,
we depend.
yes, yes, very easy question. So another question is question number 8. A pitot static tube is used to measure a velocity of water in a pipe, and the stagnation pressure head is 6 meter and the static pressure head is 5 meter. Calculate the velocity of flow assuming the coefficient of pitot tube equal to 0.98. So you just try to calculate. Here we need to calculate the velocity using our pitot tube concept.
Sir, the question is not visible. Kindly, can you show the
Yes,
question?
yes, sure, sure. Let me just increase the size. Now it is visible.
No, sir. Still, it is not.
Okay, let us read. You have one pitot tube and you need to measure the velocity in the pitot tube, and you have the data stagnant head as well as static head. The stagnant head value is 6 meter and the static head is your 5 meter. Okay, and your coefficient of velocity is given 0.98. This three data is given. Using these three data you need to calculate the velocity. Simple question.
Stagnant head is 5 meters. Static head is 6 meter.
Oh no, no, just opposite.
Okay, stagnant head is 6 meter and static head is 5 meter.
Yes, yes.
And one more data is given, sir.
Coefficient 0.98. Coefficient of velocity. Coefficient of pitot tube actually, not velocity. Coefficient of pitot tube use, that is your efficiency, you can say 0.9. Whatever you will get the final answer, you need to just multiply with 0.98. Sometimes in such type of question you will directly you will get the head, so you can apply root 2gh, but here head is not given. At the place of head you have this stagnant pressure head as well as your stagnant the static head, so you can think. And if the coefficient is given, so you need to multiply your final answer with the CD.
Sir, actually, I have not gone through that formula, right? I do not remember. Could
Okay,
you
okay,
please go to the solution? Because, see, I have been working in the water treatment field, sir, water and sewage.
okay, okay.
So, I am working. That is the reason I could not attend. I attended only one lecture, but still, I
Okay,
am
okay,
definitely, definitely interested. I have been working in this field for last 20 plus years.
okay, okay, okay. Very
So
nice, very
wastewater
nice.
treatment is my core interest, and I have been completed BTech in mechanical engineering and then MTech in environment.
Okay, okay, okay. Very nice.
So I am trying to devote some time, and some days back I was hospitalized and I had a small surgery. That is the reason, but anyway,
Yeah,
I'll
I
cover it.
understand. I understand. Okay.
That is the reason I have just came to just go into the flow, just jump into the river so that I can cope up with you.
Oh,
That's my reason.
oh, okay, okay, okay.
And I appreciate your patience that you are teaching with with your this recordings only. That's good.
Yes, yes.
That's
Because
very good.
today I don't know why no one joined today in the class. I don't know why.
Yesterday the message was already clearly put that this class is postponed.
No, no, no.
But
If you will read the message, you have the another one also.
yes, two classes were there, 6 to 8 and 7 to 9.
Yeah. So I am teaching from 7 to 9.
Right, sir.
So here you can read very clearly. We invite you to join the session 2 and get the doubts clear from the learner. So here is actually I think the session 1 was is postponed, but session 2 is I am teaching in the session 2. So I think the student bit confused. I think only
Yes, I think
refresh.
they must have joined this one.
Yes, yes, because
Anyway, sir, that is that is good for me. At least I could meet you.
yes, yes. Okay, okay, fine. So
So let us
here,
go ahead for this Peter tube, sir. static head is this 5 meter, and pressure stagnant pressure head means if it is connected to some pipe, the
Yes.
pipe, then this pressure will be working with the static head. So there will be cumulative head with 6 meter and 5 meter. What I understand is.
So
So could you please,
here you can
help me
see,
in this?
here you can see very clearly. Let me just graphical representation to show you. So here you can see the static head actually we measure using the your this one, the piezometer you can measure very clearly. The static head,
Okay.
right? So this is P value is given your 5, and here is stagnation value is given in terms of, here is the pressure, but the your final answer is, the question is given in terms of meter, so divided by rho z. Once you will divide by rho z, you will get in the meter. So
Yes,
the
definitely, sir.
stagnation pressure you can measure with your this pitot 2. So using this, this is the formula. This is the formula for your
Sir, I
value.
can see your sheet. Could you please, display that if you are showing something?
Yes, not visible.
Not, sir. You can just, just
Slide is
unshare
moving.
it and then share.
Slide is moving.
Unshare and share. No, it is not visible, sir. Only my photo and your photo is, it is unshared already.
Oh, why it is? Let me just reshare. Now,
Now it is visible, sir.
okay, okay. So let me just take the pen. So here, this is from your piezometer. You can calculate the static pressure as you can see here. And in the question is given the head. Head means the pressure divided by rho z. This is in meter. So this value is given your 5 meter, this value, and this from pitot tube you can calculate the stagnant pressure. So this value is given 6. Not p value. This 6 value is given p by rho z. P is stagnant by rho z. And this value
Right,
is,
sir.
yeah, if once we will put in this formula, let us multiply with this rho z. This is by g, once we will multiply. So g and rho, g and p. So let me just, p by rho z, let us assume p by rho z is head. If p by rho z is equal to head, so means your p is equal to what? Rho g h. So here you can put the rho g h. So rho and this g will be the cancel out. Your final formula will become, once you will read. So 2 will be remain in terms of head. I am going to write. So 2g and h. 2gh, and h is the difference between your stagnant and your static. So here just very simple things. The question number 7, where is the,
Sir, this is your question paper, or this is the assignment one you are teaching one?
no, I have the my questions also and assignment ones also, but this assignment is long back, not the current assignment.
Okay. So could you be sharing this so that you can, I could, whatever you have done in
Yes,
one,
yes, yes. So
right, sir.
you are not able to access these questions because I have already a lot of, I think week 1, 2, 3, 4 I have already uploaded. Are you not able to access?
Sir, actually, I was not regular in this class. I was regular in wastewater only.
Okay,
So that is the reason. But
okay.
I'll be.
I'll show you. I'll just show you how you will access. So let me just finish
Right,
this
sir.
question. So
Right, sir. Please.
2 and g value is given already 10. Let us assume here, and this value is 5. 6 minus 5 will be 1. So this is 20. So root 20. No, why 20 I am writing here? Not.
Sir, H is 1 meter only because stagnant pressure minus the spin is
Yes.
uh,
1 meter, and G is 9.81, and coefficient is also given.
but the velocity formula you had written was under root 2
G
uh,
H.
okay, G into this rho stagnant minus rho P
Yes.
divided by rho. Divided by rho also you have done, no?
Yeah, but rho in terms of when your value is given in terms of pressure, not in terms of head. that is Newton per meter
Okay.
square.
Right. That I know, sir. That's
Yes,
okay.
whence the value will given in Newton per meter, but here is value is in meter. So only root 2 z h. H is the difference between your stagnant and static. So around root 20 you will get. So root 20 means around, here we can guess the option D will be the correct, because you need to multiply with 0.98
Yes.
also.
Definitely, sir.
Yes, so
4.34.
only option matching this one. So okay, so how you will access, let me just show you, because this is very important, which is visible. So hopefully my screen one is visible, right?
Yes, it is visible, sir.
So you will do one thing. So just you will write here the NPTL SWAM, right?
That's okay, sir. I am getting the this emails already, no?
Yeah, email,
Okay, but
but you are not.
it
I
is
think,
somewhere else.
yes, but I think you are not able to get. Let me just within 1 minute I'll just show you, because it is
Right.
very important. You can access the all things. So fluid mechanics, and from here you need to go. So already I have registered, so directly you will, and here you can say see the problem solving session, this one.
Right, sir.
And in the problem solving session you just click on the recording problem solving session, and once you will click here you will get the Excel sheet, right? This is my, I am, this is my, right? We have the,
Right, sir.
here in this course we have 3 TA, this me Om Prakash Maurya, then Vineet, and this lesson.
Right,
So
sir.
from here you can access, this is a Google Drive. So from Google Drive you can access the everythings. So here already I have uploaded the week 1, 2, 3, 4, 5. Similar
Sir, will
for,
I be will I be able to download this?
yes, everything you can download. You can download
Okay.
for similar for Kapoor and similar for your Lusher.
Right, sir. Right.
And these are the YouTube link. Whatever I am
Or
recording.
if I do this and see your this one DocSap's that presentations means that PPTs, and I do your assignment, I can cop up with you within 2 3 days.
Yes. If you have any doubt you are asking about.
No, not for doubt, because I have not studied regularly. Now, in the initial I attended 1 2 lectures, and after that I could not do. That's why reason I'll be trying to read the whatever the this
Yes.
presentations are loaded, and your sessions.
Yes.
Right, sir.
These
Right. Please go on.
yeah, these presentation only about whatever I am teaching, whatever I am
Right, sir.
solving here, that thing only in this you will get in these PPTs.
I got your point, sir.
Yeah.
And the DAXA presentation is different, now that I can take.
Yes.
Yes.
So let us move with the questions again. So we have only 3 minutes. Let me just, so okay, let me just share the entire screen. So it is visible again. Okay, so next question is very simple. I think a pipe of a constant diameter 400 carrying water at velocity 25 meter per second, and the pressure at point A and B are given 29.43 Newton per centimeter square and 22.5 563 Newton per centimeter square respectively, while at datum A and B are 28 meter and 30 meter. Find the loss of head between A and B. Very simple question. This is just
Simple,
application.
but
Yeah.
Bernoulli is to be applied, na sir?
Yes. So let me just, for the another student who will see later. So we have the 2 point A and B. A and B, and the constant diameter. Everywhere the diameter is constant. So D is equal to, is given 400 mm. Remember please, 400 mm. And velocity, if the diameter is same, velocity will be the same everywhere. The 25 meter per second. The pressure is given here. Pressure difference is there. The pressure at point A is 29.43 and here is 22.56 something. So we will apply the Bernoulli's at point A and B. So the velocity, if the velocity is same, the v1 v2 will be cancelled out, only remaining will be the p1 by rho z, and because v1 is square by 2g and this side v2 is square by 2g, that will be cancelled out because of the velocity is same from at point A and B. So only the datum is remaining, z, and here p2 by rho z plus z, that is the ZA and ZB. And another, we need to calculate the loss of head between A and B. So whether the loss will add in the first side and second side, how you will decide, this is the very important. So everything is fine. Okay.
The loss will be, in the direction of flow. So
Yeah, in
pipe
the
diameter.
direction of flow, because here is the pressure is 29, here is pressure is 22 something, let us for assume, because
Means it is
29.
going upward. It is going upward.
Yeah,
Water is going
so
upward.
yes, so the loss due to the friction, actually loss due to the friction of the pipe. So the pressure in this side, you have the, if you will add the let us, why we are we will add the loss in this side, because you know already the, as the total head should be the constant, total head should be the constant. So if this side your the value is 29 or something za, similar the heads, because these two parameters should be the constant. When the when these two parameter will be the constant, once you will add the loss in this side, whatever you are losing, let us suppose you have the 100 and after the losing you get only the 90. So whatever you will lose, once you will add in this side, then you will get the 100 and 100, right?
Right,
So
sir.
similar thing here, yes, you will
Got your
add
point,
the
because
loss.
loss is going in that direction. If we
Yes,
add at the P2 side, then it will be balanced.
yes, then it will balanced. So
Right.
this is
May
all
HL
about,
will be added on the right side.
yes. So this is all about for today. So let us, will meet again in the next Tuesday, hopefully on 2 2 September, 2nd September.
Okay, sir.
Okay, fine. Thank you for your join.
Thank you, More sir. Thanks a lot, sir.
Okay,
You are very nice.
thank you.
Thank you.